Now let's talk about annuities. First, we'll look at the future value of an annuity. The future value of an annuity includes 4 different variables. They are payment, interest rate, N, and the future value. Remember that annuities require equal consecutive payments. And here's an example of a set of equal consecutive payments. If you invest $100 at year end for each of the next 5 years, how much will you have at the end of the 5th year if you earn 8% annually? So in this case, we have these 3 knowns and this unknown. Got the rate, the number of periods, the amount of the annuity, and we're trying to calculate what the future value is. Well, the formula is structured like this. The future value equals the payment times 1 over I to the n power minus 1 divided by I. Now, we don't really use that formula much anymore, but you could easily use it. And if you did, you'd say 1.08 to the 5th power minus 1 divided by 0.08. And that gets 5.866601 multiplied by 100, and we get 586.66. By the way, it's always a good idea to take a look at the problem before you even start and get something of an estimate as to what the value might be. So, for example, here I have 5 payments of 100, and I'm calculating a future value. Well, I know that even at a 0 interest rate, my value must be greater than 500. It must be 500. So if the rate is greater than 0, it must be greater than 500. But it's not necessarily going to be 1,000, for example, unless the rate is very high. So is 586.66 a reasonable number? And the answer is, yeah, that seems like it would be reasonable, and of course it is the correct number. Now let's take a look at the calculations using the BA2 Plus calculator. So we're going to turn on our calculator, and I'm sorry if it doesn't seem like the light is too good on this, but let me see if I can put something under it just to give it a different angle. That might work. We're going to first clear everything. So second, clear TVM, second, clear work, and I'll just hit another one just for fun. And that gets us that top line, and now our payments are 100. So 100. And in this case, it was an outflow, so I'm going to change the sign, change signs, payment. And our rate is 8%, so we're going to say 8I. And again, we could have put the N first if we wanted to, or the I first. It doesn't really matter. And now we have to put that it's 5 periods, 5N. So we put in our 3 pieces of data. Now we hit compute, future value, and we get 586.66, same thing that we had in the other version. But there are other structures for future value of an annuity. So here's a version, this bottom one, says if you need to have $10,000 6 years from now and can earn 9% annually, what size of year-end annual payments will accomplish your goal? So in this case, we know what the future value is. In this case, we didn't. But in this case, we know the future value, the rate, the time period, and we need to calculate the payment. Okay, so here's the structure. And I always think it's a good idea to draw the timeline to sort of see what it looks like. And one thing you might recognize is that the future value of annuity is just a future value of a series of individual payments. That is, this payment that accumulated at 9% for 5 years. Now notice we have n equals 6, but since the payments are at the end of the year, this payment would only get interest for 1, 2, 3, 4, 5 years. So this one for 5 years, this for 4, 3, 2, 1, and 0. The last payment gets no interest at all because it occurs at the end of the time frame. Well, this is what the formula would look like. It's the same as this one up here, only instead of solving for the future value, we're solving for the payment. So when we put those numbers into the formula, we end up with 1329.20. And using the calculator, we would clear everything. So second, I'm going to put this back under here and see if it will help a little bit. We're going to clear everything. Second, clear TVM. Second, clear work, clear everything. And we're going to put in that 10,000 is our future value. And our number of time periods is 6. So we're going to hit 6 is our N. And 9 is our rate. And we're going to compute the payment. So compute up here, compute payment, 1329.20. So that's the same number that we got in this case. Now, does that number make sense if we look back at the timeline, 1329.20, and here we see 1329.20 right here. Well, what is 10,000 divided by 6? Okay, 10,000 divided by 6 is equal to 1666.67. Well, if we put in 1666.67 every year and got 0 interest, we would have $10,000. So we know that since we are getting interest, that the amount must be less than 1666.67. So our number that we calculated, 1329.20, I can't say that it's definitely right. I know it is after calculating it. But if I calculate that number on an exam or something, I at least know that it's in the ballpark because I know I have to be less than 1666.67. So that's just a little check to help you, especially when you're on an exam. Although I recognize that it's not always easy to do such things while you're on an exam. Okay, so let's look at another type of situation. In this situation, we're going to know the future value, we're going to know the payment, we're going to know the N, but we don't know the I. You need to accumulate $1,000 in 5 years. If you can afford to invest $150 at the end of each year, what rate of return will be required to reach your goal? So here's the structure of the problem. And in this one, we're not going to show the calculations. It's more complicated than we need to do. And besides, we are calculator people. So we're going to go ahead and calculate what this is, and I can get my little footstool out of the way here. So we're going to clear everything. Second, clear TVM. Second, clear work. And now I'm going to put in my $1,000 future value. That's how much I'm supposed to accumulate, 1,000 future value. And my number of time periods is 5, so 5 is my N. 150 is my payment, but I need to change the sign because either the 1,000 or the 150 has to have a negative sign. And for me, I'm going to go with the 150 because it's an investment program or something I have to accumulate money. So I change signs here and enter that as my payment. And now I'm going to compute the rate. So I hit compute, IY, and it's 14.43%. And does that make sense that you would put in $150 a year for 5 years at 14.43% and accumulate $1,000? Well, 150 times 5 is 750. So we know we're going to have some positive rate in order to get to 1,000. Is it 14.43? Well, it is, but if we came up with a number like 82%, we would know that something's wrong. And let's look at the final version of future value of an annuity. And in this case, we're solving for N. Now, frankly, this is not one that we use very often, but it's still worth knowing. So in this case, we're going to know the future value of the annuity, the payment, and the I, and now we're going to calculate N. So how long does it take to accumulate this amount? Evelyn will begin receiving payments of $2,000 per year beginning 1 year from now. If she invests the money at a 12% return, how long will it take for her to accumulate $15,000? Well, what I've shown here is a little break in the timeline. And the reason I show that break is because we don't know exactly how long this is going to take. So we've got our N over here, our nth period, and we're trying to figure out where that nth period is. And again, we're not going to show the mathematical format for this, but we can go ahead and show the calculations on our BA2 Plus calculator. And here's how it would go. We're going to clear everything. Second, clear TVM. Second, clear work, clear. And we've got 2,000 as our payment. So 2,000, change signs, payment. We've got 12 as our rate. We've got 15,000 as our future value. And now we're going to compute our time frame, compute N, and 5.66 is the answer that we get. Now let's take a look at present value of an annuity. Now, present value of an annuity, I have to move this around just a little bit. With present value of an annuity, we also have 4 different pieces of information. We have a payment, we have an interest rate, we have an N, and we have the present value of an annuity. Now, in this structure, you can see that really what we have is the present value. In this case, we have 5 payments. We have the present value of these 5 individual payments. So we could calculate the present value of this one discounted 1 year, and this one discounted 2 years and 3 years, and this one 4 years, and this one 5 years, and then we could add them all up. Or we could solve it as a present value of an annuity problem, since they are all equal payments and consecutive payments. So this problem says if you can afford to make a loan payment of $100 at the end of each of the next 5 years, how much could you borrow today if the interest rate is 10%? So this is not unlike calculating the value of a home mortgage that you could take out, or car. If you have an amount that you can budget to pay, and you know what the rate is, and you know what the number of time periods is, how much can you borrow? So this is a very much of a real life kind of a problem. So here's our structure. And this in the brackets is actually the formula for the present value of an annuity factor. 1 minus 1 over 1 plus I to the n, all that divided by I. Well, we're probably not going to do that in an exam. Some people do it, but not me. I have a nice calculator. And if we did it, though, we would calculate this. We'd have to take our 1 plus 0.1 to the 5th power, take the inverse of that, subtract it from 1, and divide by 0.1. And if we did that, we'd get 379.08. If instead we use our handy BA2 Plus calculator, we would clear everything. And we'd say 100 is our payment, 100 plus minus payment. And we would say that our time period is 5, so 5N, and our rate is 10. And now we're going to compute present value, and we get 379.08. Now again, we might want to ask ourselves, does this number make much sense? Well, if we look back at the payment structure, the payment structure says $100 per year for 5 years. How much is it worth today? Well, if it were discounted at 0%, we would have $500 discounted back to the present, and they would, discounted at 0, would end up being $500. Well, we know it has to be less than $500, and it is $379. So does that make sense? It makes sense. That doesn't mean we have the exact answer. Of course, we do in this case. But if you are trying to figure out whether your answer even makes sense, 379 seems to make reasonable sense. Let's go to the next example. In this case, we're going to know the present value of the annuity and the I and the N, and we're going to compute the payments. Now, here's this type of structure, and what you're looking at is your typical loan. If I borrow a certain amount, and if my payments are going to be equal, and I have a particular rate, and I know my time period, I can figure out, well, how much will those payments be? So here it is. We borrow $20,000 at a rate of 7% for 6 years. How much will your annual payments be? Here's our structure. We could just turn this problem around and solve for payment instead of present value of the annuity. And so instead of having this multiplication sign, we have a divide sign over here. And if we did that, we would come up with $4,195.92. Well, let's take a look here. If this were 6 payments with 0 interest rate, 20,000 divided by 6 is equal, well, 20,000 divided by 6 is equal to $3,333. So if there were no interest rate, then 6 payments of $3,333.33 would be sufficient to pay off that $20,000 loan. However, most lenders prefer to get interest rather than to get no interest, which means we know that our payments have to be greater than this. So if you solve the problem and get the number $2,922, something went wrong. So here's our $4,195.92. And if we use our handy calculator, it would look like this. We're going to clear everything. So clear everything on your calculator. Second, clear TVM. Second, clear work. And now we're going to put in the dollar amount, 20,000. And in this case, I view that as an inflow. They're lending me money, so they're giving me, they're lending me money, so it's coming into me. So that's going to be my present value. And 7 is the interest rate, so 7 is the rate. 6 is the number of time periods, so 6 in. And now I'm going to compute the payment, $41.95.92. So same thing as when we did when we used the formula. And there's one last case for present value of an annuity, and here it is. In this case, we know the present value. No, did I skip one? No. We have it's not this. We have 2 more. Present value, payment, in. We know these 3, and we don't know the I. So we're going to have to calculate what that rate is. A $50,000 business loan requires payments of $12,000 per year for 5 years. What is the interest rate on the loan? Well, again, here's our structure. Now, in this case, when we see our $12,000 payments, and there are 5 of them, well, 5 times $12,000 is $60,000. So it doesn't look like this is a huge rate, but it's not an insignificant rate either. This is one where we're not going to do any sort of calculation. We're just going to go straight to the TIBA2 plus and do our calculation. So second, clear TVM. Second, clear work. We have a present value of $50,000. $12,000 is our payment, and it must be of opposite sign, so plus minus, enter, down. Sorry, I did that wrong. I'm going to clear this back out. Second, clear TVM. Second, clear work. I was thinking of another type of problem. Let's go with 50,000 is our present value. 12,000 plus minus is our payment. 5 is in, and we're going to compute the rate. And 6.40%. The last case for present value of an annuity shows known variables of the present value of the annuity, the payment, and the rate, and we're trying to solve for n. Again, this is not as common, but it's still valid. So in this case, Jack needs to borrow $10,000 and can make payments of $2,000 per year. If the interest rate is 11%, how long will it take to pay off the loan? So here's our payment structure, and again, we don't have a known value for n, so we have a kind of a kink in our timeline here, just saying that it's someplace out there. And it's a rather complicated problem. We're not going to use anything other than the keystrokes for the calculator. And here they are. We're going to first turn it on, second clear TVM, second clear work. And I hit it clear again. 10,000 is our present value. 10,000 present value. 2,000 change signs is our payment. 11 is our rate. Compute n, and we get 7.65 years. So this says it will take 7.65 years for you to be able to pay off that loan if you pay it at that rate. Again, this is not one that we do too commonly, but it is reasonable. I'd like to mention something called the Rule of 72. For those of you who haven't heard of it, this is just a rule of thumb, and I'll just write it out here, Rule of 72. And the Rule of 72 says if you take the number 72 and divide it by the rate, it will approximate, I'm going to put squiggly, approximate the number of years to double. Now, what does that mean? Well, let's just give an example. 72 divided by, let's say, an 8% rate, and we don't divide it by 0.08, we just divide by 8, equals 9. It would take 9 years to double. Well, let's test that out a little bit. So I'm going to clear everything on my calculator. Second, clear TVM, second, clear work. And we know 72 divided by 8 is equal to 9. So I'm just going to do a little present and future value problem. I'm going to say, what if I had 100 as my present value? And if I had a rate of 8%, 8 is my I. And if 200, no, let's go with 9. 9 is my n. 9 is my n. Compute my future value. And you see that it comes up to not exactly doubling, but pretty close to doubling. So at 8%, it takes about 9 years for it to double. Now, this works better if you have numbers that are fairly close to each other, like 9 and 8, as compared to, let's say, 3%. So 72 divided by 3 is equal to 24. Okay, well, let's try that problem. I really don't have to clear everything out here, but I'm going to anyway. So if I have 100, change signs, and that's my present value. And if 3 is my rate, and if 24 is my n, compute the future value, and it's 203.28. So that's a little bit farther off than the one before, but even so, as just a rough rule of thumb, just to know that Rule of 72 is probably fairly helpful when you're out in the field.